So a little bit about the clarity, and then again, some of these slides are going to be, I'll go over quickly because we've kind of already gone over them. The clarity EBSD detector is kind of basically our new flagship product. Of course, is the first direct electron EBSD detector on the market. Again, we've already seen these because I kind of did it on purpose, where we saw the kind of the the direct detection on film of X-ray, or not X-ray sensitive film, but of electron sensitive film, or probably just film. And of course, we changed that, of course, with the phosphor screen technology, with the lens assemblies for both the earlier cameras, analog cameras, the SIT cameras, all the way up until the CCD based, as well as the CMOS based cameras. Again, these all use phosphor screens, these all use lens assemblies, and those will, of course, introduce artifacts into the system. We talked a little bit about those artifacts earlier, with things like barrel distortions, pincushion distortions. All these exist as distortions or artifacts that exist just because they're lenses. It doesn't really matter what you're doing. Nothing is ever going to be perfect. And you will see that in relatively high definition EBSD patterns if you know where to look. Of course, the other way to go about some of these ways of getting around these distortions are doing things like fiber optic coupling, but those do their own whole things of the kind of different distortions. So if you do have fiber optic coupling, you can see things like what they call chicken wire blemishes, tapering effects, light losses. There's a whole bunch of different things that kind of happen with this that, again, you would see in fiber optics as well. So what we've done with that is basically said, hey, what if I just use direct electron detection instead? And that's what we've done over the last, I'm not entirely sure how long we've been working on this now, 3 years plus, of getting this kind of as a product. And we've released this now again as the first direct electron detection system for EBSD. So now essentially you basically count electrons instead of transferring the electrons to photons to a camera-based system. So this is not, it removes the optical path, so you have zero distortions, no phosphor screen, no lens system. It's a well-known technology. It's been used in the electron microscopy community in biological samples for quite some time. It's already been demonstrated to work with EBSD. It's nothing new. Of course, there were some challenges with this, including the sensor geometry, solid angle, and temperature, and we fixed most of those. So we've basically done it with the traditional EBSD geometry. And it uses 4 chips, 4 256 by 256s, giving us a passively cooled 5 by 12 square pixel resolution sensor. And there it is in the microscope. It's basically what it looks like. And again, it's basically in this case here, you just have your detector substrates, and you're just counting electrons. The way this works is basically it counts to get individual electrons, and because of that, the readout noise is actually very, very low, and so it's not counted. So you essentially have no readout noise in this system. You only have what's called shot noise. The event happens, does its thing, and then we get the amplifier. It's amplified, and of course it has to be over the threshold to remove the noise, and then of course you get basically a single event, and that's what we're doing. In the end, when you do this, you get pretty patterns, right? So this right here is the highly dynamic range of these patterns. They're 13.5 bit depth, and you can see very fine detail inside of these patterns because of that. And this works very well because you do have a relatively strong intensity gradient, so you can see that. So coupling this no noise and no distortion, you get unparalleled pattern quality with sensitivity that just seems almost it's crazy. Again, we've done stuff on the very, very low picoamp range. So it works for standard EBSD mapping. Here's an austenitic ferrite sample with 2 nanoamps at 50 points per second, and you can see it maps. Again, it gives incredibly pretty maps for this kind of stuff, but also incredibly precise because of what it's doing. So again, you look at this, you can see that it does good job with the phase differentiation, and also looking at fine scale deformation features. Again, we can see that over there on the CAM map. It also works at low current. This is honestly underselling the camera by quite a bit on this sample here. You can see that at 15 kV beam at 110 picoamps and 48 patterns per second, this has very little problems doing anything here. Differences here is you can see again the pattern quality. The patterns earlier today you guys saw were bad. You can already see the lines here. This is perfectly indexable kind of data. NPAR, of course, makes it even better. So again, this is at 110 picoamps on a very a kind of a normal sample. You're actually doing event counting here. You're doing this, so this makes it a a very sensitive material. So this is uh, basically a way of looking at this is again I'm counting individual electrons, but I need those background electrons to be rephrase that. I need the electrons to be over background. So here you can see that, and here I only have 50 maximum electrons. But even with that 50 max electrons, I have enough electrons over background to basically say I have patterns available here that are indexable. So here again, you can see that these patterns, this is a perfectly indexable pattern at 50 electrons basically captured per pixel of the detector. What that means is you actually can go further and further kind of down the line, but in this case, it actually kind of shows the other way around, where again, I can do 50 electrons or I can go, to 380 electrons per pixel, and I get better and better pictures. So again, this is actually basically an event counting detector at this point, because again, it's just the way it works. I'm going to kind of skip some of these, but just realize again that if you get more electrons, you get prettier pictures. I don't think that's too surprising. The signature profile, the signal profile on this is exactly what you expect. You can see that is there because again, you're looking at the EBSD signal on a background, so it's basically again what we expect. But again, it's crazy sensitive. So on the left over here, we have 5,000 electrons per pixel on average. Over here on the right, we actually have 10 electrons per pixel on average. And again, that's on average here. So this is above background. So you're only looking at maybe 7 to 8 electrons over background on here, and that is actually a perfectly indexable pattern as well. And here you can see it is indexed. And you can see again, this is mappable. This is 10 electrons per pixel at 13 picoamps of beam current here on an additively manufactured steel. So again, I can see that, hey, this is going to be pretty good for beam sensitive kind of materials, doing very fine scale work. So I mean, 13 picoamps is pretty tiny, but that's 10 electrons per pixel. I can do less. So this right here is actually at 6 picoamps. So on the left-hand side here, you can see it's having a little bit of problems. There is some data being dropped out, but it's also doing a very good job with the data it does have. Running that through RenPAR basically makes a very okay data set into essentially a perfect data set. Again, this is at 6 picoamps per pixel. Now, you guys have probably already heard me talk about NPAR, so I'm not really going to kind of talk about that too much. But again, just realize that we did use NPAR on that last data set. So there are actually some papers out there that have already used this kind of this material here. So our good old friend over at AMOF is collecting some of this data for us, and again, I've already published some of this data as well. So this right here was an early kind of data set on this kind of detector here, and you can see that it's a little rough, and that's rough because it was before some of the things we did to commercialize this as an actual product for us. You can see here that again, this is your pattern over here on the left, turned into a perfectly indexable result. Now the real question here is can I get this over a large scale area? And of course the answer to that is yes. So this right here is the halide perovskite material, incredibly beam sensitive. Most of these times, if you look at this crosswise with a beam, you damage the sample. So here again, we can see that I can actually look at grain structure and orientation structure on this and see that there is in fact a fiber structure to this material. So again, over on the left-hand side, this is a grain map. You can see individual grains, see the grain structure, which means I can get grain size over here, which we can see is on average about 10 microns. And overlook here, I can see that there is a structure, a texture to the material, and it's mostly red, which means I have a 001 texture. And look at a different direction, of course. I can see it out of plane as well. So this is a halide perovskite material. There's also these thin films, the methylammonium lead iodide films that people are working on. And this is, again, doing what's called flash infrared annealing. Again, I don't claim to be an expert on that. But again, here you can see at 100 picoamps, they're able to get high quality results on this. And of course, they're able to map as well. This is a map of this guy over here. We can see both the structure of the material as well as a very strongly textured part of this, in this case, in the 112 alignment. Again, just kind of another example of this. So with that in mind, I mean, honestly, at this point, I think it's probably best to turn it over to Matt if he's ready. Matt, are you ready?
Yes, I just need to figure out how to share my screen.
And there you go.
All right, do we see that then?
We do in fact see your screen.
Awesome. Well, thank you, Shawn, for letting me crash the party, and excited to be here. Excited to be running the clarity detector. It's running on our Tenio microscope, which has a nice link to Ohio State because it actually was at your facility a few years before, right before we got it. So it's a nice little tie-in here to the workshop. So I'm going to show a couple of different things. First, I'm going to show the basic collection, the operation, the behind the scenes operation of the detector from a shell program. So I'm going to go ahead and say, let's bring up my preview and turn on my collection. So let me move this out of the way. And so I'm just going to collect. This is just live collection. I'm going to start with just a piece of single crystal silicon so you can get an idea of how the detector works. So it's very similar to a regular EBSD detector, a Velocity, a Hikari, other detectors you might have seen, where it comes in from the side. We tilt our sample 70 degrees. The size of the detector is very similar to that of our traditional detectors. It's a little bit smaller, but it's generally the same. And that's been intentional. We wanted to keep the same form factor so we can keep things on the same ports. We use the same type of general design. If the detector gets too big, then we start to be limited on which ports can be used for EBSD. If it gets to be too small, then we have to get it really close to get the solid angle we want to capture the diffraction pattern. And so we selected this, what we call a quad detector. And so that's what we're seeing here with the live collection, is we have 4 different detectors that are joined together. So each one of these detectors is 256 by 256 pixels. And so we seam them together to get 512 by 512 array. And the size of that detector is nominally about 30 millimeters squared. And so, and again, that's all based on saying, we're taking technology and engineering it to work in an SEM chamber. So we're looking at lots of things in terms of size, in terms of heat management, in terms of throughput, to allow that to happen. So the first thing I want to show, I'm going to stop this. I'm just going to increase the exposure just a little bit. Maybe a little bit more than that. I'll go to 0.2. Just so we can start to see. Try to get that. I won't go in increments of that. So you can see that this is just a live collection, though. This is no background subtraction. You can go just a little higher so you can really see it, and then we'll go back down again. You can see you get really nice EBSD patterns. And to show you that it's live, I'm going to take it off of a spot mode. So there you can kind of see it rastering. It's a little blurrier because the beam's not in a single orientation or location. If I go back to a spot mode, you'll see that we get a very nice sharp pattern. We can look in a little more detail in a minute, but there's going to be a lot of detail. And so, as Shawn mentioned, we're removing a phosphor screen from the capture process. So, when an electron hits the phosphor screen, it generates light photons, but it also sort of cascades through there. There's not a direct one-to-one spatial location. There's a little bit of blurring through the phosphorluminescence process. And then there's no directing those light photons to the camera sensor. And so whether that's with lenses or fiber optics, there's different artifacts that can be involved. So this is just a direct impact of the electron onto a sensor. It's a silicon-based sensor, but it's what's called a hybrid pixel detector. So the silicon sensor is bonded to these readout chips. And so it's what's called a hybrid detector. So it's not something we worry about, too much exposure on the detector. It's very robust as far as a system. And so a couple of things I want to show while we're in the shell program. What we're able to do when we're running, I'm going to go over here to this little thing here, and I'm just going to say, show me kind of statistics. And as I move my cursor around, you'll see this X, Y, Z value changes. X and Y is just the coordinate, within the pixel array space. Z here, though, is the number of events or the number of electrons per pixel. So we're directly counting the number of pixels per channel. So you see, if we look at the average, Right now, we're looking at just under 5,000 electrons on average. The maximum counter here is just under 12,000. So it's essentially about 13.5 bits counter depth we have to count things. This is just important because, you know, the more electrons we count, the better our shot noise statistics. We don't have any read noise with this detector, and that's why it works really well at low beam doses, because when things are read noise dominated, we don't have read noise. And so that's why we show lots of applications that are for beam sensitive materials, and I'll show you some examples of that. But the opposite of that is we can get very nice patterns by counting lots of electrons. So you can see with this particular one, if I move my cursor here in the center, you know, we have about 6,000 electrons. It's not a flat fielded signal, so there's less at the edge. You know, it drops down to 3,000-ish up in the corner, you know, 1,300-ish. And that's one of the reasons we do a background subtraction. We'll come back to that. But what I want to show, right now I'm running at about 1 nanoamp beam current. I'm going to drop this down about an order of magnitude. So give me 1 second here as I reach over. So this is going to about 100 picoamps. And you can see our image is live, so we haven't changed anything on the collection. But if I refresh my statistics, you know, I've dropped the beam current by an order of magnitude, and the average number of electrons has also dropped down by about an order of magnitude. But you can see this still gives us a very recognizable EBSD pattern, even before background subtraction. And I'm assuming by now Shawn has probably said, you know, if you can see the bands, the Huff transform is generally going to detect the bands. And then where it gets really fun is I'm going to drop it another order of magnitude. So I'm going to go from 100 picoamps down to about 10 picoamps. And again, we've dropped the signal. You can see, you know, the pattern's a little weaker. We're dealing with less electrons. But if I refresh this, now we're down to about 60 electrons on average. And so, you know, I can come to this band here. We can see it. I put that there. You know, we're talking 100 electrons here, 124, 91. So there's not a lot of signal. We can actually go lower. And rather than do this, I'm going to just drop my exposure time now. So what you'll see here, we have an average of about 30 at this point. And why I show you that, and I don't know exactly what Shawn showed initially, but I'm going to pick out a slide to show you. Couple of things I want to highlight here. You know, I mentioned that the signal is non-uniform across the surface. It's sort of it's basically shaped almost like a circle. That's why generally a lot of our detectors are circular. And if we draw a line across that, we can see the intensity profile across that. So this is our background signal here, and then our diffraction signal superimposed upon that. And that's what we're trying to find out. So when we subtract our background, you know, we'll see something that looks like this. So this pattern here on the left is with 5,000 average electrons. We see really nice, what we call high quality EBSD patterns. What we look for are higher order lines that we see through here, details in some of the zone axes. And we see there's a lot of range from max to min when we've done that subtraction. But we can run down to where we're running with 10 electrons on average. So, you know, not a lot of signal, but even in this pattern, you can see a diffraction signal. And when we look at this, we can actually run maps with that sort of a signal level. So this is with, you know, nominally 10 picoamps of beam current, and can still get very high success rates because we can resolve the patterns because there's very low, you know, essentially zero noise in the signal. And so that's what we're able to do. You know, we're able to essentially count the number of electrons, count the electrons in the signal, count the electrons in the background, start to understand how that plays a role in different types of materials and different types of, you know, different ratios of diffraction, essentially to scattering. And so it's very good for low beam dose conditions. And so I want to just show a couple of examples of this. You've seen this one. This also works with something like lithium-ion batteries. And so these are, of course, everyone hears about these batteries. We want our phones to last longer, and we want our cars to, you know, be battery-based. And so they're looking at different cathode materials, and some of these materials have very small grain sizes. They want to understand the role of orientation and grain boundary structure. And ideally, we want to be able to do this without having to do transmission Kikuchi diffraction, just because it's easier. And so this is just an example showing sort of traditional, what I'd call low beam dose conditions. This is at 20 kV, 1.5 nanoamps. We can resolve, some orientations in that particle, but there's a lot of black areas where we're getting unresolved information near the grain boundaries, where patterns will start to overlap, just due to the fact that this is a lithium-based compound. There's a larger interaction volume. The band detection struggles a little bit. But if we drop this down to say something like 10 kV, 400 picoamps, you can see we get much improved spatial resolution on these type of materials. And then we can also use it for things like, Shawn already showed some of these perovskite organic solar cells. You'll see these microstructures degrade just under imaging conditions, but we can use our tools to go to low doses and collect orientation maps. We can use it on things like rocks that are essentially non-conductive, but we can go to low enough doses that that's not an issue for us. We can do things still, it can be used for things like TKD, transmission diffraction. And this is important because we can do it at lower beam doses. When we're doing TKD work, we're looking at an electron transparent thin foil. So as we put beam current into it, if we have a lot of beam current, that starts to cause some, essentially some drift effects from the energy dosage in there. And so by doing TKD at lower beam doses, we can still get decent acquisition speeds, high spatial resolution, but we minimize some of the drift effects. And then, of course, one of the big hot topics everywhere is additive manufacturing. This is an example from a stainless steel alloy. We get a rapidly solidified structure with some cellular structure that really helps to provide superior mechanical properties. And so, by using the quality of the clarity patterns, again, they're distortion free, they're blur free. We can do cross correlation results to really improve the angular orientation precision of the technique, and couple that with improved spatial resolution compared to XRD based approaches. And we can resolve out, say, where the geometrically necessary dislocations are present. So in this map here on the top right, we can see the dislocation structure. And we've compared things like this to TEM images, and we can see how the cell structures compare and compare favorably between those. And then in addition to that, we can get really nice high quality patterns. This is from a range of materials. And this is important because EBSD is starting to move towards comparing with simulated patterns. So we have a module we call OIM Matrix, which uses dynamic diffraction simulation to generate a simulated diffraction pattern. We can compare that to an experimental pattern. And you can start to imagine it having the detail available, having the quantitative intensity information. We can start to compare our model to reality and then tweak our model and start to detect changes in that in a real pattern. So that's all exciting ways of doing it. So I wanted to start here in the shell just so you could see what's happening in the background, because we do some corrections to hide this crosshair in the system. This is just what's actually happening to the detector. So I like people to know what's happening. So I'm going to go ahead and close this. And I'm not going to save that. I'm going to fire up Apex here. All right, this is just about ready. So I don't know if you've seen the Apex software yet or not today.
They have seen Apex. I ran them through basically maximizing the velocity, which takes about 6 minutes to do correctly.
Yeah.
Let's go ahead and maximize it. Click, we're good.
Okay, and then while we're here, I'm gonna go from a single crystal sample to a polycrystalline sample, just so it's a little more interesting. But I like to do the single crystal to show the detector without anything going on. So I'm gonna go ahead and insert the detector. And while we're doing that, you'll see that once we have the clarity running, it looks very similar to what you've seen with the velocity or the Hikari. Basically, we can adjust what our pixel resolution is or what our binning level is. I'm going to jump over gutter factor. We can adjust the gain or we can adjust the exposure time. And so we've tried to design our camera system so that it's easy to jump from one to the other. The other thing we're able to do is, we'll go to binning in just a second. I'm going to go ahead and get us some, probably what I'll do is bump up our beam current first, because I don't want to wait when we're, okay. So I'm just going to get a signal here. I'm going to collect the background. So you'll see we have this correction here. I'm going to go ahead and put the microscope into a spot mode so you can see the patterns. So this is after background subtraction. You can see in our camera tab, we see the background image, we see the live pattern, we see the background corrected pattern all through here. You'll see we have what we call this gutter factor correction, where we can adjust the intensity basically to minimize the distraction of seeing that in the pattern itself. You know, we do cross correlation. We generally position the regions of interest away from those crosshairs. Doesn't particularly cause any issue, and it doesn't cause any issues with the Huff. And so you can see we get really nice patterns as we click around. We can get indexing rates just under about 100 points a second. So we can use it similar to what we call like our DigiView level scanning speeds, 100 points per second. But we can also collect data at those speeds with our full pixel resolution image, the 512 by 512 pixels. When we're saving the data, we're able to save these into a file. All the data is saved into an HDF5 structure as well, so we can organize the project through here. So we can get very nice patterns. If we come over to our pattern tab, let me just get kind of a field of view here, make sure I'm in focus. Now I'm going to kind of make this a little bit faster. Let's see, what did I do here? I did something it didn't like. The joys of a real demo.
Geez, Matt, already breaking things, huh?
I'm already breaking things.
First week out of Christmas, and Matt's breaking things.
I take full responsibility. Won't be the first time, and it won't be the last time. All right, let's do. It's probably because I have the SG shell open in the background. That's probably not going to help.
That'll definitely do it.
That is not going to help me anywhere.
Yeah, trying to control the SG shell twice at the same time is not.
Yeah, that helps understand. That's why that's doing that. I should kill both of them. Sorry about that, everyone. That's definitely not what I want to do, because that will kill both processes when they're trying to talk to the same board.
Matt, while it's laying up, I was talking to Shawn a little bit earlier about the FSD integration on these a little bit.
Yep.
I was wondering, since it's going to be a slower camera, I figured that could be more important as a feature. So what kind of changes have been there? I use the velocity the most. So I don't really use it at all for that. But
yeah, I mean, the main thing, so we've put a forward scatter detector on here. Right now we have a single diode. It's towards the bottom, so we get mostly the orientation type contrast. We have made some improvements on the amplification system, so it's more of an automatic approach rather than, I'm not sure which one you've used. We used to have kind of two different sets of brightness contrast sliders, and tweaking them in could be a little bit of a exercise of patience and humility. So now it's more of an automated process. Just get an FSD image from these. It's similar to most of the new velocities, but there may have been some that there's been a little bit of a difference. But it is still compatible with our Prius signals where we select different regions within the screen, but that's mostly for during, what's saved concurrently with data collection, and also what we do for post-processing analysis of saved patterns. So we'll bump this back up to. All right, hopefully I'm just going to get us all right, so I'm going to drop this down a little bit. Put the background, collect an image. Give the image so it's at least semi not so bright. So you can see we can now kind of click around. We can index the patterns. We can collect chemistry. I'm set up. I don't know if Shawn showed the different layouts. I can do just a basic layout where I'm just clicking back and forth. I generally will use this layout where I can see more of my indexing statistics while I'm doing stuff, and I can adjust the camera. But we also have a layout where we can go straight to EDS if we want to collect EDS data at the same time. So I was doing earlier today. And then you can see there's some here that are different names. I can customize these and save them as a layout for whatever I'm choosing to do. So it's really easy to get high quality patterns. This is great for phase identification. It's great for strain analysis. It's great for comparing with simulations. There's lots of tools in Apex for playing with this. There's tools in OM analysis for using this. And then we can also go ahead and say, I want to go to higher binning levels. So for something like this, I can go to 5x5 binning. We have this cumulative binning turned on, so it's summing the intensity. So as I turn my binning up, I drop this down to get a comparable signal. So then I can collect my background here. So now when I'm looking here, you can see similar to what we've seen on other detectors. When we go to a little bit smaller resolutions, we can get higher speeds, but still get high quality patterns that are very indexable for both traditional mapping, but can also be used for saving it at any type of resolution. And then the key with this is, again, if we look at some of the information, just if we look at profiles across different bands, there's just more contrast information through there. So we see this as a really EBSD physics type of a tool where starting to understand what are the intensity profiles across lines, what do changes in those profiles tell us. We can now measure them with more precision and more quantitative electron information. So the level of detail that's available is just significantly higher, which is really an open door to say we can really start to explore the physics of EBSD pattern formation better. And there's things that are just like, let me see, this is an interesting one here, where if we see that the pattern starts to become more diffuse at the edge, we know that's not due to any lens artifacts. Now we know that's due to the electron beam passing through the material on the way to the surface, and it's interacting with whatever defect density is there. So the sharpness comes from a higher defect density. So we can start to think about, can we correlate sharpness with that defect density as a metric of material quality from a single pattern. And we've done other things. This is looking at just standard CAM maps with some of the high quality patterns. This is showing around an indent where we're looking at standard CAM maps. And we can take this data and do cross correlation results to start to resolve higher angular resolution CAM maps, or different stress maps in different parts of the stress matrix there. So it's a really unique detector compared to legacy detectors. There's a different level of type of information that comes through there. And that's why we're looking at other types of indexing engines like the dictionary indexing to use more of the pattern information. And that should help us do things like resolve pseudosymmetry problems, resolve domain polarity issues, because we won't necessarily be limited just to the Hoff where we're looking just for bands within the diffraction image. So I think those are the main things I wanted to show. I mean, I can show watching a map's pretty boring, but we'll collect a map. This is just like our standard mapping. As we go ahead, we see the bands, see the band detection, the Hoff, the indexing, the crystal. All that's available depending on what you want to see. If you like to see both, you can kind of move your workspace around to watch things. And you can dynamically see what's happening during the map. If I wanted to see, say, my Prius center image, I can see that as it's being developed. So we see some orientation contrast in that image. So it's a nice dynamical workspace to work with. It's kind of an upgrade from our team software. So we're excited for people to be able to use it. Any questions? And like I mentioned, we've seen applications for solar cells, batteries. We've had people wanting to use it for ceramics, where they can go to low doses, geological type materials, these strain measurements in different metallic systems, phase ID applications. I think it's going to open quite a few new routes. It's really the first new technology type of an approach to EBSD detection, going back to the roots of direct detection with film type of stuff. So really high quality type issues. And with that, of course, it ties back into, it always comes back to sample prep. So we've been using some of the Gatan PEX ion beam tools to try to really get pristine surfaces, so that what we're now able to measure actually represents the actual microstructure and isn't a sample preparation artifact.